Imagine measuring pure, abstract space without physical rulers or any real-world scale. We need a way to force a perfectly illuminated grid onto that void. That is the function of the Cartesian coordinate system. It takes an empty mathematical vacuum and gives any arbitrary point within it an absolute quantifiable identity. But students usually encounter this system through rote memorization. They are handed the distance formula, the section formula, and the equations of a line as separate rules, which often creates a fragile understanding of the mathematics. The reality is that every algebraic equation used to navigate the coordinate plane exists as the shadow of a basic geometric shape projected onto the axes. To prove this, we can discard the textbook formulas. We are going to build the complete mathematical system of coordinate geometry from scratch, using only right-angle triangles. Mastering the grid requires translating geometric truths into modern algebraic notation. Take two arbitrary points, A and B, plotted in different quadrants of a Cartesian coordinate system. To calculate the exact linear distance between them using only algebra, we first have to find a familiar shape. We drop a vertical line down from B and extend a horizontal line across from A until they intersect at point C. This projection creates a right-angle triangle, allowing us to invoke the Pythagorean theorem. The length of the triangle's horizontal base is exactly the difference between the point's x-coordinates, x2 minus x1. The vertical height is the difference between their y-coordinates, y2 minus y1. Substituting these coordinate differences as the lengths of the sides, the theorem dictates that the distance squared must equal the sum of their squares. By taking the square root, we arrive at the generalized distance formula. If one of our points is the origin, 0, 0, the subtraction becomes redundant. The zeros cancel out, reducing the calculation to the square root of x squared plus y squared. Every calculation of the distance formula resolves to a restatement of the Pythagorean theorem operating within the grid. This logic also solves the problem of localization, such as finding the coordinate for a cell tower placed along a direct pathway between two nodes. The challenge is to find a specific point that divides the total distance in a fixed ratio, represented as m to n. We need to find the unknown coordinates of point P, which internally sections the line segment AB into that m to n ratio. We can bridge the gap by dropping perpendicular lines from each point straight down to the horizontal axis. Because the main line segment is a transversal cutting across parallel vertical drops, the internal angles of these two resulting triangles are identical. According to the law of similar triangles, their horizontal bases must share the m to n proportion. We define those bases algebraically as x minus x1 and x2 minus x. This establishes our equivalence. The ratio m over n is equal to the ratio of the coordinate bases. Cross-multiplying the denominators flattens this into a linear equation. By expanding these terms and grouping the x variables, we find the unknown coordinate x is exactly mx2 plus nx1 divided by m plus n. The same symmetrical logic applies to the vertical axis, giving us the y-coordinate without further derivation. Dividing a spatial line is essentially an exercise in scaling similar triangles. When a finite segment extends into an infinite line, it eventually crosses both axes. We define any infinite line using its slope and a single anchored point, expressed through the generalized point-slope equation. In practice, mathematicians look for computational optimizations, ways to simplify an equation to make it more efficient. The most effective optimization occurs at an intercept. Because the line is crossing an axis, one of its spatial coordinates is forced to be precisely 0. In algebra, a 0 instantly eliminates bulky terms and simplifies the expression. If we substitute the y-intercept coordinate, 0, c, into our generalized equation, the x0 term disappears. The equation collapses into the slope-intercept form, y equals mx plus c. We reach the limit of this optimization utilizing a line where both intercepts are known. Entering two zeros into the two-point algebraic form triggers a massive reduction of terms. This leaves us with the intercept form, x over a plus y over b equals 1. Each variation of the linear equation represents a specific engineering choice, choosing a starting point that exploits a 0 to simplify the calculation. we have mapped a blank, unmeasured void onto a defined computational system. Calculating distance is the Pythagorean theorem operating in a coordinate disguise. Sectioning a line is a direct application of the rules of similar triangles, and the famous equations of a straight line are algebraic optimizations engineered to exploit zero values. The power of coordinate geometry is that it requires no memorization once these underlying geometric axioms are understood. By translating pure geometric shapes into algebraic coordinates, we reach exact computable solutions for any point on the plane.